Now you know what they need to do.
Oh, I'm really hoping is that they solve
Now
it.
move to the top.
I haven't looked at the question.
I'm telling you what's going to happen. You will get an email saying, if you get an invitation for a talk in Italy, just refuse.
I don't know if I need new glasses or
You will not leave Italy.
like legitimately really small.
Exactly.
Telescope. You should say something at one point. It does give you an avenue to join Euclid. Yeah.
Good. Thank you.
Again, I'm oversubscribed. No, like.
You guys don't switch now to these mics or anything, we'll catch it.
At least for one, you need to do also for your position. Is that the bar for your position?
Well, it's funded.
It's fine.
Yeah, so
No, it's fine. It's a new.
Yeah, and it is new. Yeah.
It's different, I guess.
It's very different. Even from DESI, it's very
give it to them.
different. Figuring out how to.
Yeah, from this one.
Okay.
Yeah. Much harder.
These are
Much harder.
so we will need.
So how many rotations you
Oh.
have? This one is zero.
Yeah, so then that's the nominal plan is 4 rolls,
But the clicker will still.
180-degree flip, and then just a small angle. So we were just talking about, we're not sure that we need the small angle, and then kinematic lensing people would actually really like that angle to be bigger. But always it'll definitely be the 180 flip between, but then maybe we can open that up a little bit.
All right. Thanks everyone for coming back after lunch. So right now we have a panel discussion on recent cosmology results from the recent surveys, and also looking forward to future surveys and what the implications are for Roman. And so, yeah, we're very fortunate to have a panel of experts here on kind of spanning, maybe not all of the surveys, but as many as we could get for today. And so, yeah, so you saw Martine Coche's talk earlier today. So Martine, and then Ashley Ross is also here, Eric Schweitzer, Rachel Mandelbaum, and Henk Hoekstra. So, and maybe I won't say which surveys you're on yet because that'll come up on the slides that you can speak to. But what we're going to do is first just give a couple slides, or maybe even a single slide in some cases, updates or sort of overview of what the surveys are and what kinds of results are coming out of them. And then in the next part, we will move on to questions. There is a poll that you could, let me see if I can also, actually, yeah. It'll be up on the screen shortly. But I also just posted it in the general channel of the symposium Slack. So if you want, if you didn't get a chance yet to add your own question, or if you want to upvote someone else's question that was already there, please do that now if you'd like to. So later on, after we've gone through the slides, we'll turn to the questions. And then, yeah, we could even take some live questions too, but it's kind of nice to know what are people most interested in so we can kind of prioritize, because there's all kinds of questions that we might want to pose to this panel. So, all right. Okay, yeah, so I will go ahead and, oops, sorry. Kind of already went through this. There's the QR code if you want to go directly to that. All right, so I guess turn it over to Rachel.
Yeah, hi everyone. So I should say, as a caveat for all of this, I didn't have the opportunity to consult with other members of the collaborations that I'm representing who are here. So apologies for any omissions that are entirely my fault. So for HSC, just as context, this survey was meant to enable a wide variety of scientific goals, and what I'm talking about is specifically the HSC weak lensing and large-scale structure analyses, which is a subset of that work. We are still analyzing the full final data set, so what I'll talk about is our lessons for the last major cosmology analyses that we did, which were for the year 3 data set. There's a website that summarizes the initial HSC year 3 results, including the catalogs and systematics tests, but also the main cosmology analyses, which are shown in that plot on the right. Since then, there have been a few other cosmological analyses of note, one led by Tomomi Tsuneyama, and one that came out just in the past month with 2 papers led by TQ Zhang. So I would say in terms of like the major scientific challenge for this analysis, it was calibrating the redshift distributions for our tomographic samples. Given the depth of the sample, we made a sort of conservative cut in terms of not going too close to the detection limit. I have 24.5, but still that, you know, in terms of the available spectra, the calibration of those redshift distributions was like the single largest scientific and technical challenge that we faced, especially above redshift 1. I listed a number of organizational challenges, and I was trying to think of things that, you know, can sort of be like addressed for Roman, right? Like what's the lesson learned? And so the reason for mentioning the NFZ issue is because I think having better spectroscopic training sets and also, you know, reference samples for cross correlations will be really important for Roman. And likewise, for the major organizational challenges, I think there are lessons that can be learned that inform, you know, the preparations for the Roman analyses. So these included things like, you know, as anybody who's been involved in some of these analyses knows, like there are a huge number of connected projects, you know, setting up the catalogs and making sure you understand everything you need to know before you do the science, and coordinating all those connected projects and the shared software infrastructure going into them, you know, was a significant effort, including things like blinding strategy. Are the blinding, you know, the blinding approaches joint across projects versus independent? Recognizing people's major investments of efforts in a wide variety of ways, like leadership roles and, you know, big talk invitations and things like that. And, you know, even just a self-consistent review of many papers coming out at once. Avoiding single point failures is a huge issue. Having codes that can only be run by one person is not fair to anybody, either that person or the other people. There will inevitably be problems from that. The balance between openness to new ideas and new algorithms versus, like, at some point you do have to decide and say, okay, I'm using this and moving forward no matter what. And I feel like there were a few areas where we need sort of different choices and how much to wait for the new method versus, you know, just call it. And making sure that image processing, which was carried out by a different group, was sort of, you know, being well coupled to what our needs were and making sure they had the requirements for our science. So I'm sorry, I don't know how long you intended me to talk.
No, that's
sorry,
great.
That was
yeah.
too long. But yeah, I feel like these are all areas where, you know, there's an opportunity to really learn from this for Roman. And yeah.
Cool. Is this also you?
Yeah. Yes. So they had been in a different order in the slide deck. I just sent you my 3. So, like, I don't know if you want to talk, like, this is a future thing. Do you want to do all the current ones? Maybe?
Yeah,
I don't know.
It's a good idea. Let's do it that way. Yeah.
Okay, yeah, so I shown this already, so I thought it's still good to remind you because it's been out already several months and people are still talking about sigma 8 or S8 tension. Of course, just having a result which doesn't show tension, of course, doesn't remove it, but I think it's important, to sort of realize that there are other surveys going on, because I think that is something we sort of see, that the danger of large projects is that you sort of get the tunnel vision and sort of only look at what the people in your team are doing, because they produce so much information, tech notes, papers, that it's understandable. It's hard to keep up with the literature of other teams. But I think that is still, I think, very, very important to be aware of what is going on, and of course also learn from what our teams are doing. And so a lot of the things that Rachel said are very relevant. So basically, even though the change in the result is a mix of more data, the redshift calibration or improved redshift calibration played a key role. And then we have the advantage that we're a bit shallower, and even then it's hard. So I think this is, something that will stay with us for quite some time as we go to the next generation of surveys. So the advantage of KIDS is that of all the teams, it's the smallest. So that really makes communication a lot easier, right? Because on the flip side, there's Euclid, which is arguably, well, at least one of the largest, right? And that's a completely different way of doing it, but we're trying to get at least lessons learned from how surveys shouldn't have done it or should do it as much as possible. And indeed, as recognition is a very important one. So I think, especially as we transitioned, we saw things that particular Planck had done, which clearly caused trauma by some people. And it took quite some time to sort of say, no, we're not going to do it that way. We're going to do it differently. So it's very important to get these things right from the start, because some people really suffer if you don't do this right. So I think the advantage of KIDS to Euclid is that, of course, if you have a small team, it's easy to make decisions. But I think it is a challenge for large teams to say, oh, let's do this by committee, because then you'll never get anywhere. So there is this tension, right? Sort of like deciding something now. So some things have to be decided. We now have to decide on software, because maybe if you do the next slide, right? This is a Euclid timeline, and we are starting the DR1 processing right now. So if somebody comes up today with a brilliant idea that would solve all our problems, we would still say no, right? Because we can't implement it right now. So this is something which, again, it's also be clear to people, but at the same time, we want the flexibility that we can ingest new ideas as we go along. But the reason I wanted to show this is I think it's good for people to be aware of this timeline, right? Because that arrow is not the planned launch date of Roman, but that's the pretty much fixed data release 1 of Euclid, right? So I think it's important for people to be aware that there's a very big data set coming very soon, and think of the synergies that are possible, or things you can learn from that as we go along. So I think that is very important to be aware also of how your project fits within the bigger picture, where we can work together and build synergies and not just duplicate things. I think, did I have another one?
Yeah.
Oh yeah, and because that schedule, if you go back, you can see that the schedule has a sort of stretchy timeline, because my DR1 should have been launched plus 1 year, so that should have been July 1st, which is not October. So basically, we clearly think slip, and I think the next one was just to show whatever you plan for, there will be surprises. So these are some of the things that have been shown, stray light, the X-ray selfies we take, but also initial problems with the fine guidance sensor, which created beautiful pictures, but not what we wanted.
Yep. All right, thanks. Well, actually, yeah, we could do DESI.
Yeah, so I was just going to focus on a fairly narrow example but I think has been a pretty big part of DESI's success, is just that we really have consistently used the same software through all phases of the project, and in many scenarios, but a very specific example that's very close to what I do is that the fiber assignment, the code used on the mountain to determine which fiber goes to what galaxy right before we take an observation. We use that same software to actually run randoms through it and determine the footprint for DESI. That plot there shows our rather complicated footprint, which that's actually now, and because we we actually daily verify that we get the same result from fiber assignment on the mountain as we do at NERSC, where we process all the data. We can be sure that we're using actually the exact same software that gets the exact same answers with everything. And so the accuracy with which we know our footprint is basically the accuracy with which that fiber assignment code tells where the positioners where to go before then the telescope dynamically figures out where to tell them, not where to go, the telescope and all its instrumentation and software dynamically figures out where to go, and that's better than 1 arc second. So, the resolution in which we know our footprint is better than the resolution you can actually see in that plot, and that's why it gets so grainy. And there is this effort going on in Roman, and it's more difficult because things are more distributed, including the software actually on the cloud. But people are making this effort already now, and this effort will definitely pay off down the line. So keep pushing it on. This is my
All right. DES.
Oh,
Yeah.
thanks.
Go ahead, Martin.
Okay, so you saw many of these slides before. So DES is a large collaboration. It's over 400 different institutions there, and it's doing quite different science cases, from clusters, supernova, with lensing, and so that in itself is a challenge. My feeling is that DES has become a test bed for stage 4 really, and I see many people here that have been doing critical roles in DES and are now in Roman, in Euclid, myself, other people. And so the first few slides were just flashing things that I showed before: cosmic shear, BAO. Yeah, the next one there. This is the one that I didn't talk much about, which is clusters. In DES, we also do clustering, and that's the way we combine cluster abundance, cluster clustering with the rest of the 3-point. Yeah. In addition to weak lensing, mass calibrations of clusters. Yeah. And then in the last slide, I wrote down some challenges that I could think of. Definitely the most important is photometric redshift as well, because everything else that I have seen is challenging, but it gets resolved. But photometric redshift is always the one thing that it ends up dominating the error budget in a way. And there are no follow-ups, spectroscopic follow-ups, dips, and you don't see it, or at least I don't see a lot of activity in that, which is super needed, right? We have super massive imaging surveys and photometric data, but the spectroscopic one stays always the same. The other thing that is useful to keep in mind is that this is a very complex exercise. So you really, there are so many moving grounds, moving pieces. It's very hard to advance everything in parallel, because many people depends on what somebody else is doing, and so communication is critical. Having simulations, that is something that takes a lot of time to develop. By the time you realize you need the simulations, you also realize you don't have the time to develop the simulation. So thinking that in advance is very much worth it. And also, my feeling after having coordinating different groups in DES or in Euclid is that this is becoming the era of the technical cosmology also, in addition to precision cosmology. So it's very technical. It's very difficult to understand what the other people the team next to you is doing that is affecting you. And so when it comes to resolving one problem, you find something is not working out. Sometimes it's very hard to understand at the technical level what the other people is doing. And so there is this risk of disconnection, and there is fewer and fewer people that is able to understand everything that's going on. So that is a risk as well. And those people are needed when it comes to solve problems, technical problems. Yeah. And in terms of challenges, I think, so the second point goes back to what was mentioned before. This setting global timelines realistically is very hard. When you have to do that, you have to say no to new ideas, for example. And maybe at the end of the day, that timeline is not realized. Things take a lot longer. These people that had this new idea was push out. And so that's a potential, and that's a penalty that you pay. So setting global timelines is always very hard. We have been setting timelines all the time, and we always have this conflict. Decision making in very large groups is also difficult. There's always people that it's not happy about it, but okay. So I guess the issue is finding the spot in which everybody is equally unhappy, and then. Communication, as we said before, there is never enough communication. It's tricky. Even trivial things you need to communicate. So something that we have done in DES is trying to favor the leadership of early career scientists. So in our papers, there is always, typically there is a student or early postdoc leading them. And it's very hard to find the same person doing almost the same work. Year 1, year 3, or year 6. So we always rotate. And that, I think that's good because that helps training people. But you also pay a price that that new person has to learn. So finding that balance is also another thing to keep in mind. Yeah, and then conflicts and tensions and issues, problems all happen. So you need to be prepared for that to find a clear procedure to resolve those, which I think is what Ken mentioned before. So I don't know. Those are the things that I came up with. I have a longer list.
Eric.
I'm Eric Schweitzer from NASA Goddard Observational Cosmology. My primary work is with the Roman Space Telescope, wide field instrument testing, characterization, and pipelines. But for the panel, I'll also be wearing a CMB hat. So these slides were joint with Joe Dunkley. First here is a slide from her summarizing ACT and Simons. So ACT now has results for the primary CMB and increasingly high sensitivity results for secondary CMB, so lensing and SZ over half the sky. There are many opportunities for cross-correlation that are interesting for large-scale structure surveys, and there are public products to support that cross-correlation, lensing maps, Compton Y, the blackbody CMBs, that's both primary and KSE, cluster catalogs, likelihoods for cosmology combinations, and also extragalactic sources, so dusty galaxies in H1. The ACT data are all public, and Simons is committed to regular public releases in a similar fashion. And software are also public. There's an emphasis on using Jupyter notebooks and data schools to broaden the user base of those products. There are MOUs in place for several surveys, and one possibility to evaluate is for work there for Rubin, or if that could all be done with public data. Next slide. So I'll talk more about the organizational aspects maybe in the context of some of the questions, but one thing I want to mention with the CMB surveys is that we struggle not to call these experiments, so they are fielded in many different stages, and one of the interesting challenges with these surveys is fielding multiple instruments, multiple focal planes, and managing their calibrations over time while also reaching a consistent answer. So this slide shows both ACT and SPT, and you can see picking up from the Planck measurements and going down to very small angular scales. So these ground-based measurements have now reached the level of Planck, and in terms of parameter constraints, and provide a check of lambda CDM on those scales. A finding from both ACT and SPT is that there's not evidence for a lensing anomaly that was found in Planck. And the S8 tension is also melted, and I have that in the next slide. But one other question I wanted to raise for discussion is how we approach human factors when there are parameter tensions. That might come up naturally in some of the questions. Next slide. So this shows two interesting parameter planes. The left plot is buried slightly in Appendix G of the ACT results paper. And this shows visually nicely the complementarity of different cosmological probes. So here you can fit the CMB data with a hard prior that H0 is 73, and then see how that is manifest in the CMB data. So it's a little bit hard to see in the upper panel, but in the lower panel, you can see that the model shows some additional ripple relative to the data, and that's something like a 4 sigma tension. So the origin of that is that the CMB provides a very strong constraint on the angular scale, but to be able to explain that with H0 of 73, you need to shift omega matter, and that shifts the baryon matter loading, and then gives that sort of ripple shape, which causes the discrepancy. So if you squeeze one part of parameter space, you can test where that shows up in other parts of the space. And then on the right is an S8 related plane showing CMB lensing in pink. So it's fairly degenerate between sigma 8 and omega matter, and then CMB anisotropy, which allows a constraint on omega matter from constraint of epoch of radiation equality, and then sigma 8 through the both lensing and the anisotropy amplitude to give a sharp constraint there. And then another measurement from the CMB are SE clusters and cluster counts, which have a light degeneracy direction kind of along lensing, but do allow a definite constraint of omega matter and sigma 8 through the counts. Yeah, that's it for me.
Great, thank you. Why don't I go back to desk? Yeah.
Okay. DESC is a collaboration that's preparing for the cosmological analysis of data from the Rubin Observatory LSST. And I think, some key aspects of DESC were informed by the Rubin Observatory landscapes. I wanted to just mention that. The observatory construction and operations is formally distinct organizationally and financially from the LSST science collaborations, which are 8 independent entities that are preparing to do science. And that barrier, organizational barrier has, informed some of the preparation for science. I should emphasize that there are people who work on both sides of the barrier, but, it still has an impact. DESC is preparing to do science with multiple different cosmological probes towards better understanding of dark energy, dark matter, and other fundamental cosmological questions. And it includes both probes of structure growth and probes of expansion history. So type 1a supernovae and like weak lensing and large scale structure are both very important probes for DESC that if you look at that parameter plot, it's a little hard to see, but they break some degeneracies in the high dimensional cosmological parameter space. So some key aspects of DESC and how it's been preparing for science. So I was collaboration spokesperson for 2 years, and before that I was analysis coordinator for 4 years. My predecessor as spokesperson, Phil Marshall, used to say DESC is a construction project. We're not building an observatory, but we're building software, and we're building a collaboration that's ready to do science with that data. And at the time, initially when he said that, I thought that is super cheesy. But I do think, I think it's true. I think time has shown that it's true. We do have to build both of those things, and a lot of work has gone into doing so. There are multiple different large-scale software efforts that are incorporating, individuals who bring expertise from multiple different precursor survey collaborations, which I think has been really important. I think you're going to hear, I think, TQ, are you giving a talk about rail tomorrow? Okay, so you'll hear about just one of them in the area of photometric redshifts tomorrow. But there are multiple different efforts like that try to incorporate, lessons and algorithms and expertise from precursor surveys. It's formally distinct from Rubin Observatory, but an important effort has been building and then, managing, curating the relationships with the observatory team to ensure that, the cosmological science is going to be what we've all been hoping for and working on this project for. And that has included things like determination of the survey cadence, the observing strategy. That has been, more than a decade of community input through the observatory, seeking community feedback on like specific questions and iterating towards an observing strategy. And there's a committee that's a Rubin Observatory committee, but that includes members of the science community who are liaisons to the science collaborations. And giving input into that has been super important for DESC. And if you look at the current observing strategy, there are key decisions that were made that were driven by well-defined concrete input on the quantitative impact of observing strategy on the cosmological science. One important focus for DESC has been developing the relevant technical computing and analysis approaches that are needed for Rubin data through the production and analysis of simulations and through analysis of precursor survey data. And that's something that I think has been really important both for getting software pipelines in place, but also making sure, for example, that early career scientists could do work in this collaboration that doesn't have data yet and get credit and get important training, right? They have to be analyzing and getting their hands on data, ideally both simulated and real. And some of these large-scale simulation efforts, there's a Data Challenge 2 simulation effort that took a lot of time and a lot of people's cycles, and it was designed to do particular things, so it doesn't do everything that you would want with simulations. But one of the really important things it did for the first time was getting some of the computing and some of the analysis working groups talking to each other really actively about what are the needs, right? And building connections and building pipelines that get that information together, which is something we're going to need in the long run. And so I happen to be currently one of the website maintainers, including our automated publication list. And there are 100 papers up on that website, from before Rubin commissioning even started, and that reflects the fact that it's been a multi-year intensive effort to build the analysis software that incorporates all that expertise and algorithms from precursor surveys. And from my perspective, I'm thinking of where we are right now in playing with Rubin commissioning data versus where we were in HSC commissioning. In HSC commissioning, we had a single weak lensing shear algorithm and a single PhotoZ algorithm that we were struggling to run to do some initial analyses. And with Rubin commissioning data, we have 3 state-of-the-art shear pipelines and like 8 PhotoZ codes that have been run on commissioning data, and that happened right away. I mean, and it's like just a huge difference in terms of the level of preparation for this data set. I mean, there's still plenty to do, but it's great that we are where we are now.
Yeah. Thank you. All right, so then I think go back to the Roman slides. So yeah, I guess Ashley.
Oh, I think I already. Yeah, I was thinking of them as pretty linked. So yeah, talking about just the links across the different groups in Roman. We've got the PITS, and we've got the Science Support Center, and we've got the SOC here, and I'm forgetting what that stands for. And then we also have all the project information that we get from all the testing at Goddard and the thermal vacuum test and everything. So a lot of great work going on everywhere, and then we have to connect it all and make sure we're all consistent. We're all using the same code, the same version of the code, all that, and and we're going to get there, and the efforts to get there are that many people are making are of vital importance, and that'll keep going. And this is a harder problem than we have in DESI, where it's pretty much just NERSC and on the mountain. But the fact that we make that work in DESI has made everything work really well. And and we're already using software that's developed here, and that's been super useful for the pit. And I'm assuming things like PyCF will continue to be developed and continue to have the latest optical model and all that. And it's super useful that it has that, vital that it does. Seeing the presentation on the Roman research nexus, and I had logged into that in the past. I think that's something that all of us can think about trying to use to facilitate this. Even if we're not going to do large parts of the analysis there, just thinking of simple consistency tests that anytime there's a code update from anybody, you make sure it goes there first, and you make sure that everything comes out consistent across all these centers with the varying code, and that everything works. And then maybe you go and say, okay, this works here. I do the same test on NERSC, make sure I get the same result. Then I go forward and do my larger analysis. I think that's something that might work. And just an example of testing across platforms. We actually had a recent issue in DESI that was super annoying. I mentioned the daily test that we do. We demand that the fiber assign returns the same results on NERSC as it does on the mountain, that we get the same assignments, and that's vital to everything that we do next, basically. And we had a software update, and this wasn't happening. It was like one assignment that was different, but that's infinity to us. And it turned out that's a change in the software for some reason caused these floating point errors in the trigonometric functions with involving small angles to blow up and give us this instance. And we eventually figured out how to fix it. Lots of headaches, but it's worth it in the end, because now we know we're consistent and we can go forward again. Why it took 4 years for that to happen, that's something to have some reflection on as well. But one lesson is there's very funny things, exactly what's going on with what each compiler used for your software. And so trying to do this across 4 platforms instead of 2, you can imagine this goes up exponentially. But so you just really need to do these tests and make sure everything's consistent and make sure none of these things bite you in the end. Is the main message there. So I focused on this really specific thing. There's tons of lessons throughout all the collaboration culture and all that, and you should there's lots of DESI people here that people can talk about, and maybe when we get into questions, people in the room can chime in as well. But I was just focusing on this narrow issue.
All right, and for the record, SOC is Science Operations Center.
Yeah.
But it's a bit of a loaded term because in the context of the symposium, it's also Scientific Organizing Committee. So yeah, when I would meet with the Scientific Organizing Committee, I had notes that said SOC. I labeled them. So, okay, next is, Rachel.
Okay, so you've heard a lot from me, so I'll try to keep this one shorter. So the high latitude imaging survey cosmology pit is focusing on going from Roman images to cosmology with large scale structure probes, and the group that is working on this is relatively small compared to, say, the group working on comparable efforts in DESC. And so there's a focus on pipeline building and on using proven technology from previous surveys or from DESC where possible, and then developing just the Roman specific aspects in the pit. And of course, there's plenty to do to get those things tuned and validated for Roman, but it means trying to have a good starting point where possible. Only build something new if you really have to build something new. And the pit has a wide variety of ongoing activities depending on the analysis step. In a few cases, there's sort of basic research needed to develop the algorithm, but there's also a lot of work that involves assessing and comparing different approaches, that are already implemented and out there. I believe the inference group is doing a data challenge now or in the near future, for example. Assembling proto pipelines using existing software, but then that sort of enables you to then work on the Roman specific parts of them, and testing and improving the software using simulations or precursor data. One of the things that's sort of come up recently is, the computing infrastructure and understanding the different computing infrastructure needs for, cosmological analysis versus basic image processing, and what does that mean for the computing infrastructure used by this group versus, the Roman project. I guess the reason I'm mentioning that is just because it's been in my mind recently that, sometimes people say, oh, well, we need this many million CPU hours, but all, million CPU hours or whatever are not the same. Sometimes you need very different architectures to enable the work. That's been a pretty relevant factor for us recently.
All right, thank you. So I think we can move over to discussion. Yeah, moving to.
Let's thanks first our. So I'm gonna.
Also, a quick question while you do that. Are there like supernova people in the room right now? If you raise your hand. Yeah, okay, we do have some. Okay, so sorry, there wasn't a slide specifically for you, but it would be great if you feel comfortable to hear from you at some point on perhaps some of the questions that come up. So yeah, all right. So you don't mind if I pick on you later? Okay, great.
So I'm gonna flash this slide for a couple of minutes more, so people have the opportunity to vote the questions that are there or type their own. And I'm gonna leave it there 30 seconds. So, sorry about that. Pop up. And in the meanwhile, our speakers can take a breather.
We need those little bottles.
We need the bottles of water. Right. 30 more seconds.
And maybe one other comment is, because there are people on WebEx, right? If people online want to, you're always free to use the Slido poll, but if you'd also like to ask a question, feel free to pop it in the chat and we'll occasionally ask if there's anything in the chat.
Right, 5 more seconds. Alrighty, the pressure is on. So let's see what the people decided. All right, so one question with 20 up votes. So what are the biggest challenges for healthy collaboration in cosmology, and what has worked well for building and maintaining it? Let's start with Martin.
Thanks. What is the biggest challenge? Can you say that again?
So what are the biggest challenges for healthy collaboration in cosmology, and what has worked well for building and maintaining it?
Let me think.
Sorry for putting you on the spot.
Yeah, conflicts will always appear, right? I guess there are different levels of conflicts, no? I mean, if there are serious ones, like harassment or things of that level, that has their own channels that proper prepare should take care of. But then there are conflicts regarding to recognition or who does with which paper, and I think it's important to prevent conflict and trying to be aware of what's going on in the group, trying to talk to people in advance. Because sometimes you see something is going to end up in a conflict down the road, and just trying to listen to people and also putting yourself in the situation of that. Sometimes sometimes we have the experience to see that some things will not have consequences, but maybe in the views of somebody that is younger or that have something more things to risk, then the perceptions are completely different. So I think it's very important to put yourself in the situation of the other person and try to understand and to listen. Sometimes there are conflicts coming from the senior people, and those are more difficult to handle sometimes. But eventually things move on, right? We have had conflicts in the ES, but has been resolved to a degree. Like prevention is what I would say.
All right. Thank you. Same question. Let's see. We'll try to go in this order. I also picked let's go to our supernova PID colleagues. Do you want to take it?
Sure. I think communication is always key. And what Paula said previously, all the groups are engrossed in what they are doing and their particular science, so sometimes we have blinkers on with regards to what everybody else is doing. Mm-hmm. And to be honest, right now, speak to each other about what everybody is going through in their different situations is very important. So yes, communication is key. Trying to look at things from the big picture and not narrow down so much sometimes to find those equal, equality between different people is important. And creating an open dialogue and a supportive environment in which people feel able to communicate is always very important.
Thank you. Same question for Ashley. You've been not only in DESI but also BOSS and SDSS before, so you can speak from those perspectives too.
Well, so I guess maybe to think about it, a specific example, again, one thing we've learned recently in DESI is that our publication policy has a little too much room for interpretation in it. It's caused a changing of the exact rules for what can qualify you for authorship on the key papers, which is important for a number of people. And so we would have probably all been better off if we had just been really clear about that in the initial publication policy. So when developing these publication policies, even though it feels like you have to be some lawyer with coming up with all these scenarios, it actually can be important down the line to just be really clear and seemingly pedantic on these issues, because that tensions arise when there's things that are unclear and then people are seeming to make arbitrary decisions, et cetera, et cetera. So you want to try to remove there's always going to be some, but as much as you can remove seemingly arbitrary decisions for things that end up being important, like authorship on key papers, you want to do that.
Thank you. Yeah.
I'm wondering if we could hear from members of the panel the second part of that question too, about building collaboration. Mm-hmm. I'd be really interested in hearing about that part too.
Good.
Well, collaboration meetings, meeting people, talking, making connections. That's all super important. Making sure, I think one thing that's nice that we started doing in DESI on some telecons, that there'd be new people would try to get people to themselves a little bit. If you're senior, being proactive, and when you see somebody have a kernel of an idea that could develop into something important, reach out and really encourage them to develop it more. Both out of selfishness, because you need these things to get done, and it helps to get more people in there, but also that just having more people involved and feeling good about everything helps too.
Yeah, I would say trying to keep a healthy atmosphere is critical as well. Trying to avoid competition, bad competition, right? And in particular for early career scientists. And so how to exactly do it, I guess it depends. But for the more senior people, just keeping an eye that there is a healthy environment is important.
Someone raised their.
I was just saying that providing opportunities through which people can collaborate is typically beneficial. So, data hacks, or, something where people can share information. So a workshop or some session is typically a good way to, like you're saying, this meeting, even getting people involved, just creating opportunities for those connections.
Yeah.
Nico?
Or maybe also collaborations that already exist, but like Roman already exists, but there are new people coming. So there is this divergence between the newcomers, and then you make the collaboration such that people can easily adapt. I think that's very important because otherwise there's like a group of people who know things, and then everyone is like, how do I do science? That's one way.
Yeah, creating single entry points to information is important.
Onboarding.
Yeah, onboarding, yeah.
Thank you. So, Eric, from your vantage point of view of like CFD world and Roman, like more within the project, what do you think about this question? What are the challenges for a healthy collaboration in cosmology, and what work well for building and maintaining it?
Yeah, I may continue on the theme of credit and visibility, and especially thinking about instrumentation, testing, commissioning, pipeline, things that happen early in an instrument's life or mission. And there can be kind of two aspects of this. One is citations, and one model for that could be through citation blocks. So if you use a result, that there can be, say, a block of text that provides citations to key calibrations. I think Sloan may have pioneered this. I don't know if others may be able to provide the definitive there, but a block that you could put in a paper. So that way more obscure papers can continue to be acknowledged for the role in results. And then another is on authorship, and this becomes a slightly different set of considerations for open science also. So if there's a code base that many people are contributing to, think about ways there that you could have a registry of contributors and thresholds for which there be authorship in publications using that code, and similar for reference files or other data. So one approach that CMB instruments have used is identifying a builder role. And one nice thing about that is that often instrumentation folks move on to other things, but that builder role maintains connections to people who had worked on the instrument. So it's a way to reach back if things come up in understanding the data. For building a new team, I think onboarding is a key aspect there, and data hacks and things to really get your hands dirty with real data and analysis rather than kind of abstraction are great. And one thing that's very nice within Roman hardware project is there's a large database of through TDMS, our internal document system. There's an enormous database of documents to get up to speed. Let's see. Another aspect of building a team is that there are multiple roles from the instrument teams, data processing, science users, and one related to building a team is establishing a sort of stewardship model of information across those phases and groups. So who's responsible for which aspects? And it may not be a clean like interface control document delivery, but more of a stewardship of that information as especially as new people join.
Thank you. Anything that you would like to add, Rachel or Hank?
I can't say this is the biggest, but definitely a big one is something I alluded to earlier, but I wanted to comment on the how do you overcome it. At some point you have to decide this is the algorithm I'm going to use for this key analysis, and maybe you decide that some other algorithms aren't performing well enough, or maybe they actually look like they could perform extremely well, but they're not mature enough and they need more work and they could be used in future. Like at some point, there needs to be a decision so the group can go on and do science and not just sort of leave it open. And doing that in a way that works well for everybody is really challenging, right? The people who were working on algorithms that maybe don't turn out to be ready for prime time, right? Maybe they should be worked on in the future, and there has to be a way to incentivize them to continue that work. Or maybe it turns out that they're just not going to work well enough. There's a fundamental limitation. They still need to get credit for the fundamental contribution they've made towards the group's effort on this analysis, which is extremely important, and they need recognition and credit for that. And there needs to be ways as well for people to come in and say, like, I do have a new algorithm and I want to spend time working on that, and maybe that's for a future analysis, and for people to not feel threatened by that, but rather welcoming of that, right? And so for that, I would just go back to what we heard earlier. I feel like communication is key. When I've seen this go most badly wrong, it was because somebody went in with assumptions that were unstated. Like they came in and they were like, I want to show you my great new algorithm, without saying, I think this is a really good candidate for future analyses. And then somebody who's doing a current analysis is, threatened, right? So I think, being explicit about what these efforts mean to the collective efforts of the group is really important, and not ambushing people. People maybe should get a heads up, that we're going to talk about this or that. I think all of that is really important for maintaining trust, in what the group is doing together.
Thank you. Hank, anything to add?
Yeah, so I think communication is something we have been challenging with, because it's both in terms of making policies and making them clear. As in Euclid, we have publication policy, and we make deliberate choices there. And for some people they're good, for some people maybe not so good, but the idea was really focused on basically giving maximum recognition to whoever does the work. But in the end, there can only be one first author, or right. So that, and you can see people often come up with, but this is, why can't we do it like 10 corresponding authors or so? And they're like, but read what the policy says. So this is where you try to have a solution, but people don't even read about it. So you have to keep repeating and explain why the choice has been made. So there's often people might be upset at first, but once you explain that we sort of predefine these projects with the intent to avoid conflict, right? So you can't have anarchy, because then people will just end up fighting, but that the idea is to sort of also not to restrict people, but to have find a balance as we go along. I think it's very important. And that also makes sense to sort of build the community, is also to say, well, we don't want people to just submit papers with the result, but you should be very early on within, right, in this, the right subgroup, start saying, I want to do this. And in principle, everybody can join, so keep it open, but at the same time, people should not be afraid to be, and I think Rachel mentioned trust, that they trust others enough that they don't quickly start scrutiny. So we try to minimize the opportunity for that, but also try to sort of have people be open and sort of say, look, you can just have your idea, and people think it's a good idea, why don't you go ahead with it and encourage them to do that? But that's the challenge, and bringing also people across the survey together. So it's communications in many different dimensions. It's something we definitely struggled with initially. I think it's getting better, but it remains a challenge.
Thank you so much.
I was wondering if you could say more about Euclid policy as evolved from Planck and lessons there.
Yeah, so one thing we at the publication policy, because that actually quite some time ago, is to not have alphabetic authorship unless so so we have like flagship papers, so papers where you say, look, so maybe the most highly cited result, say, look, everybody contributed, right? We're not going to have the discussion on who should be first author. It's alphabetical, and the lead author, the corresponding author is the PI. Of course, with the overview paper, we really broke that rule, but once, and we will never break the rule again, because that's why the PI is the lead author. But otherwise, it's alphabetical. But if possible, the authorship reflects the work, the people that did the work. So we want, and that was an interesting discussion, because everybody wanted flagship papers. You don't want to be the lead author of the flagship paper because it's alphabetical. So it's kind of funny when people, once you explain the situation, they realize, they are really summaries of the papers that really present the new work. And so it's an ongoing work, but that is, I think, a big change from Planck. So it's as little as possible alphabetical authorship. And then we have different groups with builders and so on, but it's up to the team to figure out how they want to do their authorship. So that may lead to conflict in the future, but for now it's sort of worked fine. But I think that is a big change. And I think another big change is, and I think that will help Rubin as well, you can do so many things. So initially you would see people like, oh yeah, but I want to do this, and that person wants to do the same. So they were afraid for conflict. To be honest, even though we have like thousands of people, we don't have enough people to do all the science. Like, so certain science is of course more popular than other, but it's surprising at the end of the day how much you can do with these data. And so once people start realizing it, then either they split up or they work together. Actually, one thing that is maybe good mentioning is, because it was explicitly mentioned, so one of the I think highlights of Q1 is of course the work on strong gravitational lenses. And that was initially right, because everybody can have their favorite lens and so on. There was potential of a lot of competition, but actually that group of research basically realized there's too much, that there's no way, that it would be pointless to compete. And they actually came together and decided, look, let's work together because we can accomplish a lot more than that. So it's basically the sheer volume of data forced them to actually come to their senses and actually do really great stuff. So I think that some of it happens by just flooding people with data.
All right, thank you so much. So the next question, I think this might be only for Ashley, maybe someone in the audience too. But are there lessons from DESI and SDSS efficient data and analysis delivery that can be applied to imaging surveys?
Yeah, so first, somebody take a screenshot and send it to Michael Levy, please. But yeah, well, so look, we can work back from the delivery of the Y3 BAO results, which honestly, I'm still shocked we did that less than a year after the Y1 BAO results. But you know, the idea to try to do that was essentially conceived almost immediately after obtaining those Y1 results, and then communication started happening about, well, what would we actually need to do in order to deliver that? And the answer was not change anything at all. Basically, just give us the data from the Redshift pipeline, deliver that, verify it, pass it through all the same checks, but essentially change nothing about the analysis. And so that's like a kind of decision that Rachel alluded to earlier. We weren't going to change the BAO fitting. We weren't going to change the way we did the covariance matrices. We weren't going to change the way that we process the LSS catalogs, the way that we determined their systematic weights, as long as everything was essentially passing the same metrics that we were seeing. And so that's how you can produce the results a year later. You can just trust that all you need is more data. And honestly, it was the right decision. If you look at all the results, they still pass all the tests. BAO is amazing because imaging systematics, other systematics really don't impact it very much. You might have noticed we have not released the the rest of the results yet. That work is ongoing. It requires more care. And then, but yeah, working further back, so internally, definitely some people would have said it took a long time for the year one results, though I often would say, well, look how long DES is taking. But some things that helped were, being not only making these decisions, but also having different ways of doing things. For instance, when we started year one, we assumed that for the covariance matrices, we'd be using mocks like we had throughout SDSS. It turned out that being able to use those for accurate covariance matrices really required having the accurate fiber assignment run through all the mocks, not just a subset of the mocks that we had run on Y1. But in parallel, this Rascal C method that Jade applied to Roman mocks, as she showed you earlier, had been developed and tested on both early data. We put out a BAO measurement with the first 2 months of the data using that method, and then it got more on both the detailed mocks and the approximate mocks, and looked like it was passing all the tests that we needed to. So we had, when the mocks weren't going to work for a covariance matrix, the other method was. So that allowed us to, move forward and deliver both the Y1 and Y3 results using a different method. So having, even if you think one particular method is the ideal method, having a diversity of methods that might achieve the final result and fostering all of those so that you can have some flexibility definitely helps that. Not that other groups aren't doing that, but that was a case that really helped us in DESI. But yeah, honestly, the biggest thing though is just that the observational systematics in BAO are continuously proven to not be nearly as much of an issue as they are for lensing measurements. Yeah.
So for the next one, we'll try to have like sentence each, and what aspect of the raw calibration worries you the most? I will start with Hank.
I guess this is Rubin.
Yeah, I'd like to hear your thoughts on Rubin.
So the one word I haven't heard this week, but I may be wrong, is persistence. So that's something, if you have Mercatel, that is something that is there, and well, you have better ones than we do, but still, and I think this is something that we're definitely still dealing. I think we're making progress, but Roman is the first telescope that is going to try to do cosmic shear with infrared detectors, and this is something I was sort of curious about. So this is something I would probably worry about the most for Roman, but I may be completely wrong because I use CCDs.
Our supernova.
Yeah, I was going to say burn-in or just any sort of count rate nonlinearity.
That's good. Yeah.
And to add on that, how they all kind of fold in together to each other, and therefore how they are analyzed within the pipeline, and what exactly is included in the pipeline, because there are potentially some of the degeneracies that we're seeing. How do we address that as a whole? We don't want to, have an L2 product so that we'll have to go back to L1 because it's not including something that we're concerned about. So that's my biggest concern.
Thank you. Rachel?
So like Hank, I come from CCDs. So I would say I generally get anxious about any of the detector effects that are in these detectors that aren't in CCDs just because it's new to me, not because, some of them are extremely well characterized. So I was thinking about it. I don't think of I have an answer worth. Sorry.
No, it's fine. Eric?
Yeah, maybe to build on the detector effects, one question is the concept of operations for how the SRC is used to characterize the detectors, and then how that flows downstream. And then maybe not quite at the level of raw images. The other calibration area I consider is wide field chromatic response and field dependent of the PSF, both for supernovae and photoz's, but also for weak lensing that Federico described for the PSF. So it's near the pixel level.
Thank you. Ashley?
Yeah, these variations of the PSF, and well, you know, we're hopefully going to, like I talked about in the talk, look at how much this wavelength dependent PSF matters in the spectral extraction. But then, yeah, if it matters a lot, that makes our simulations a lot harder. So you know, there'll be an iterative process there. But and then I guess just, you know, more broadly, you know, paying attention to all the details that we need to, making sure we're getting all the information to the correct people, and ultimately in the simulations, making sure that we are considering all the effects that could be important down the line.
Martin?
My background is a bit different, but I guess from the standard things that we always discuss in Euclid or have been discussing in DESI is what has been mentioned already, no? Chromatic effects or persistence, or chromaticity of the PSF and so on. Cannot add much more to that.
Thank you. All right.
Should we switch over to maybe audience questions?
Yeah.
Oh, there's one.
Kind of our last.
There's one online.
Okay, great.
Could you minimize that update message again?
Yeah. It's it keeps popping up. Sorry about that.
No, it's okay. Are nonlinearities in individual pixels being characterized, modeled, and compensated for?
I think that's for us, bro.
Well, you might want to say what's in the sock pipeline.
Yeah, so in the sub pipeline, there is a linearity correction that corrects for nonlinearity pixels, and it's like pixel by pixel. And there is currently, it's a polynomial-based solution, but like we are open to other solutions. And I think that the project also has a similar approach. Maybe are you doing pixel by pixel as well, right, for T1? Or
Yeah, I mean, it depends on what it is, but we also have a bunch of test data that we're taking for ground characterization of our flight detectors at different levels. And so we do a number of analyses that do look at nonlinearity. Some of them will not be applied as a default because, you know, not all science cases will really rely on those questions. But for some of the specific science goals, then, you know, for example, some of the PIDs will go in and do maybe some further implementation of some, you know, nonlinear either correction or modeling or folding it in somehow. Yeah.
Thanks. Any questions from the audience?
Yeah. So on the Rubin side, so I'm part of the calibration team in the Rubin data management. So just super quickly, I think for weak lensing, some of the worries are the better effects, but of course we're using it. And like lateral E-field as well, these sort of things. But one thing I'm scared about is how I see how difficult the pipeline is in the Rubin data management. And it's impossible for people who are going to use those data to know what went in details in those pipelines. Like, I think it's even within the end, people don't know what the other is doing. So I guess even things like detecting objects or correcting the backgrounds, like really kind of like basic things that are going to impact the measurements that we're going to use. And I wonder how much we should be scared about that. I guess for Euclid and Rubin, it's the same system as well, right? It's people are dedicated to processing things over data and receiving it downstream. So is the hope that when we do cosmology, we take those effects into, like, we kind of like characterize any dependence on like selection effects, or like we kind of model any things that might have been going on in the pipeline, like that we catch those certain things. I don't know how we're gonna do it.
I'd be happy to on that. I mean, I think that part of the thought process, you know, behind like sheer measurement algorithms like magnetic detection is that, yes, there's going to be things happening in like object detection and selection that will, you know, result in various selection biases. And we can't completely eliminate that. So we directly calibrate that using the data. I feel like that's, you know, the Anacal method that Shang-Chun Li has been leading is a similar, like conceptually very similar. You get the sheer response of all your steps, the detection and selection and so on, precisely because it's impossible to control all of those things.
Yeah, same for Euclid. We try to simulate the whole process and then check whether the simulate. So we're really trying to make the simulation data look like the observations. So that's the advantage. Once you have observation, you can do this. That's going quite well. Confident. But of course, there's always things that you might not have anticipated. But again, yeah, we haven't seen actually.
Any more takers on this question? Right. Sorry.
Yeah, go ahead.
Yes, I have a question for all the panelists. When managing a larger project that involves, how do you assign credit to the idea, the technical work, and the effort to organize?
Yeah, so for Euclid, we have a tracking thing. It's not necessarily the way it has its downsides too. My original idea was to auction off work packages, so then the lowest FTE would get it, but that was considered too capitalist. No, we basically try to assign, basically you say, I spent this much work on it, so that's one aspect, so you gain publication credits, that's one thing. But at the end of the day, right, it depends a bit on the task, but right, there are with data releases papers, so people get recognition there, but we also encourage people to write papers on it. And then that's the one way to get recognition. But we also try to, right, in talks, get people that put in particular effort to give talks, etc. So we try it as much as possible. Can't make it perfect, but we try to showcase what people are doing also within the consortium. But yeah, this one way is to just generic tracking. So you do know, or when people really have made major contributions, they can become builders. So that is also something as a clear recognition. And then something which is actually quite good. I don't know if Roman has it, but we have at our consortium meeting so-called star prizes. So to recognize different categories, so instrumentation, or team efforts, but also early career or PhD students. So specific categories where we say, look, right, because it's also hopefully that's the aim to inspire. You can see a PhD student spending some time doing something quite interesting for the project, and so that gets recognized, and then hopefully other people say, look, I want to do that too. So there's different ways to recognize it.
Yeah. So one thing that in DS we do often is to be very wary of the important meetings like WAS or APS, and sometimes we try to time the release of some papers before those meetings, so the people so people leading those papers can attend those meetings and present, and we really encourage and give support to those people to participate in. And also same thing with application periods, right? So you want to be very aware of when is the application period starting and trying to make sure that the papers that can be released. And if you are thinking on a batch that can be split in papers that are already there and waiting, just go ahead and submit. So that's one thing. The other thing is that for our alphabetical papers now we decided to make contribution statements in the papers. So most of our papers are not alphabetical, but of course the ones that are more important ones are alphabetical. And we have this come up with a procedure to add contribution statements split by category. And we will try to enforce that. That's the way the collaboration is showing and recognizing what different people have contributed to papers in those cases that they haven't lead the paper, but it's not that just they're signing because they are builders, right? So they have done some contribution. Yeah.
Anyone else wants to add anything?
Yeah, so I mean, first author papers is still like, the biggest thing for people. And so one thing is just be creative about what can be a first author paper. If you've got 4 excellent people and they're all still working in the same area, that doesn't mean there can't be 4 first author papers in that area. You can carve up the work and do it. And, there's been cases where, and sometimes for the technical work, it can actually be, people might not see how it will go into an actual first author paper. And, so there's been a couple of cases where, someone's been doing excellent work and I've said, you should write a paper. And what paper would I write? And then, I'd come up with an outline for them. Here's the paper you could write, and then they did it. So, but that needed to happen. So I think just constantly thinking about that, because that's ultimately what most people want, helps. Obviously you can't have infinite first author papers, but usually you can identify the people who are early career scientists working nearly full time in your area, and every single one of those people should get first author papers. If they're not, you're not doing your job. So.
Yeah. Another category that's useful is a leading author. So if you have a sort of tiered author list where maybe one person led the majority of the writing, but then there's a smaller group of people who made major contributions, and calling that a leading authorship as still a very important role. But then, assigning responsibilities to work is challenging, and one thing that can help guide that is through precursor studies. So somebody's already working on a simulated analysis that can feed into sort of a pipeline for clear authorship on the major publications.
Well, I agree with what a lot of the other panelists have said about the various ways to recognize effort and contributions. So I won't bore you by repeating it, but I will just add one thing that I think is an important responsibility of working group leads and other people in leadership roles and collaborations, which is, there are always going to be, maybe a postdoc who's like shy and not able to advocate for themselves, or a grad student whose advisor is, not noticing they need to advocate for their student. And those people shouldn't get shafted and lack recognition just because of those circumstances. And I think it's important for the leadership to not just hear the people who are saying, oh yeah, I want to lead this, science paper because I made these technical contributions, but also look around and ask like, who's contributing really well and actually should be getting recognition, but they're not pushing it, right? And look out for opportunities to recognize them.
Awesome. Thank you so much. I think it's 3:08. I think that our panelists must be exhausted, so let's give them another round of thank you. Thank you all for voting and participating. And now we have our coffee break. We'll resume at 3:40.